The strong nuclear force is the name of the force that holds the protons and the neutrons together. And if you think about why this is important, we've talked about how positive and negative charges attract. But like charges repel. So negatives repel, but also positives and positives repel. And so in order to keep those positive protons happy in the very, very small nucleus, the strong nuclear force kicks in. The strong nuclear force is one of the four fundamental forces in nature. This is an overview of the four forces of nature. Now, gravity, the gravitation force, is the thing that holds the planets around the sun. It keeps our solar system circling the galaxy, and the galaxies is circling each other in the universe, all that kind of stuff. It's a powerful force, but it is relatively long range. Like, it works great about holding the moon to the Earth's orbit, that kind of jazz, but it doesn't do a very good job, say, holding you and me together if we were next to each other. So it's considered to be a weak force. Now, it's not that it's not like a wussy force, because wow, yeah, holding the planets around the sun is no small feat. However, it is a relatively long-range force, and when you compare gravity to the other forces we're going to talk about, it's one of the weaker ones, which is strange. Another force of nature is called the weak nuclear force, and it is a force that's responsible for giving beta decay. So every time we're going to talk about beta decay, it's basically due to the weak nuclear force. We're not going to talk too much about the weak nuclear force, but it is a relatively short-range force. It's not as helpful to us as the next two forces are, so honestly, I'm going to kind of gloss over it, but in physics, you'll talk about it a lot more. But the third force is one we've talked about extensively since Chem 221, and that's the electromagnetic force, or the EM force. And the EM force is considered relatively long range. It's the force that keeps electrons around the nucleus. And sometimes I've called this the glue that holds the atoms together. I don't know if you want to use that or not, but that is something that truly helps. All those positive, negative attractions, that's all the EM force, which is pretty cool. Now, the EM force, they feel is 10 to the 36 times more powerful than gravity. So when I said gravity was weak, no disrespect to gravity, because it is important, it keeps us on the earth and stuff like that. However, it is much weaker than the electromagnetic force. Electromagnetic force is nothing to mess around with. Again, all the times I've mentioned Coulomb's law or Coulomb's forces and electromagnetic, EM, all this kind of jazz, that's all positive, negative. That's the electromagnetic force. But the fourth force is definitely going to be something to talk about. It's called the strong nuclear force. And the strong nuclear force is about 1,000,000, 10 to the 6, times more powerful than electromagnetic. Now, electromagnetic, as I said, was 10 to the 36 times more powerful than gravity, and EM is even, or strong nuclear force, is even stronger than the electromagnetic force. So strong nuclear force is what keeps those protons next to each other in the nucleus, because positives and positives don't want to be there, but the strong nuclear overpowers them. However, the strong nuclear force has a very short range, and they feel it's about 10 to the minus 15 meters. It's a femtometer. That's the Greek prefix for 10 to the minus 15th. You don't need to worry about that. The important thing for us is that it's very, very short range. And we're going to see in this chapter that sometimes the strong nuclear force starts breaking down. Those positive repulsions in the nucleus start interacting, and it's going to be enough to break a lot of the atoms apart. However, as long as the strong nuclear force is active, it is a strong force. It keeps those protons and neutrons together. You can think about it as the glue that keeps the nucleus together. So while electromagnetic keeps the electrons around the positive nucleus, and that's a type of glue, there is a second type of glue here that keeps the nucleus together. So we'll talk about the interactions of electromagnetic and strong nuclear forces in the upcoming sections. Some nuclei are very, very stable, but there are a lot of nuclei that are unstable. And the reason they're unstable is because the electromagnetic force, which is relatively long range compared to our other force, the strong force, the electromagnetic force begins overpowering the strong force. So the strong force keeps those positive protons in check in the nucleus, but when it starts breaking down, the positive electromagnetic force, those protons interacting with protons, protons and repelling each other start to build up. They build up like friction, if you will, and it's going to be enough to break the nucleus apart. Now, you do get some stabilization through what's called magnetic dilution because neutrons are neutral. And if you can have a neutral neutron between two protons, that does tend to separate them a little bit, and it does offer a little bit of stabilization. So we're going to see that the number of neutrons in the average isotope of an atom tends to increase as the atomic number goes up. Up to calcium, the most stable nuclei usually occur when the proton number is equal to the neutron number. And there are exceptions, but generally that's the case. So for example, carbon-12 has 6 protons, atomic number 6, and 6 neutrons. So the protons and neutrons are the same. And there are some exceptions to this, but overall that's pretty good. Now past calcium but up to lead, the most stable nuclei definitely have more neutrons than protons, all right? The number of protons becomes less than the number of neutrons. And you're just going to see that the neutrons are starting to help with this magnetic dilution. All right, it tries to keep the nucleus stable. But after a while, when you get past lead, essentially all isotopes are unstable, all right? They just will all break down. Now, sometimes people consider it's beyond bismuth, but recent studies have suggested that bismuth is unstable too, so that's why, generally speaking, it's beyond lead. All isotopes are unstable and radioactive. Now, sometimes the isotopes won't decay for like millions and millions of years. You can talk about their half-life. However, the important thing here is that they will decay. They are unstable. And the timeline reference point definitely has to be considered. Like, is it our lifetime? Or the lifetime of the universe? This kind of stuff. But past lead, it is considered that all isotopes will decay. Scientists have studied this behavior about stable nuclei and the unstable nuclei. And on the x-axis there, you have the number of protons, or the atomic number Z. On the y-axis, you have the number of neutrons N, all right? So protons plus neutrons would be mass number. And if you look at this graph carefully, there's black dots in the middle and red dots on the outside. All of the black dots are considered to be stable nuclei. And so those nuclei aren't going to decompose. They're very stable. There's been no evidence that they break down, anything like that. However, on both sides of the stable nuclei, there's several red dots which represent unstable and radioactive elements, and those will break down into different kind of processes. So if you use your imagination a lot, this particular graph right here is called the peninsula of stability graph. Now, a peninsula is a part of land that juts out into a lake, and so all around the peninsula you have water, all right? So in this version, the peninsula of the stability are the black dots. It's this little tiny part of land, if you will, that juts out from the mainland, and all around it is the ocean, though it's not really an ocean, but it is called the Sea of Instability. So all of those red unstable isotopes surround the stable ones. So again, it's called the Peninsula of Stability in the Sea of Instability. And it's kind of a poetic kind of imagery that maybe pops in your mind, and that's what it's supposed to do. But you can see that as of looking at this graph, there are limits to how many stable isotope atoms there are. However, some great research has been done by some powerhouses of this field, and the two names that are most important, in my opinion, are Glenn Seaborg and Ken Moody, and they've studied these really super heavy elements and what they have, and they were the ones that helped recognize the peninsula of stability in the Sea of Instability. However, they have made predictions, and this is based on math, and it's definitely beyond our capacity here in Chem 222, but they have made predictions that there will be one day some islands of stability found. And the islands of stability will have true stable nuclei, very, very large atomic numbers, or a huge number of protons. But there's some evidence that suggests that this could happen. So eventually one day you might be able to use an element with, say, 250 protons or something like that. Right now the periodic table goes up to 118 protons. So imagine imagine having something with 250 protons that you could use like aluminum or carbon. It's pretty cool. So maybe one day we'll see, but it is fun to think about.